Now, I want to remind you what we did last time. The basic message was, if you have a sequence in a set, and the sequence has a limit, the limit must be, doesn't have to be exactly in the set. The limit has to be close to the set. If you have a sequence, doesn't have to be always in the set. Frequently is good enough. You understand? Frequently is good enough. And any limit of that sequence has got to be close to the set. Then what happens if you have a sequence in a closed set, if a set's known to be closed, and the sequence has a limit? Then the limit has got to be close to the closed set. Where are you if you're close to a closed set? You jolly well in it, right? Because a set is closed if and only if every number close to it actually belongs to it, you see? So a sequence in a closed set, or even frequently is good enough, in a closed set, if the sequence has a limit, then the limit has got to be in the set. You understand? Just wanted to point that out. We also did something much harder last time. I said if you ever take a number that is known to be close to a set, then there will definitely exist a sequence in the set whose limit is that number. That was harder, with all sorts of stuff with 1 over n's and axiom of choice. Talked about it for a long time. Did it? Yes? Right. So let me tell you something. If a set is not closed, then there's a number close to the set that doesn't belong. Isn't that right? Well, then there would be a sequence in the set that has a limit not in the set. Isn't that right? Let's suppose a set fails to be closed. Then there exists, choose a number called Charlie, close to the set but not in. Well, Charlie is the limit of some sequence in the set. There would be a sequence in the set whose limit is not in the set. You understand? Actually, a set is closed if and only if every sequence in the set that has a limit will have its limit in the set. And I wrote this up as a kind of summary last time. And I just want to draw your attention to the material from that lecture. But actually today we're moving on. And today we're going to do a theorem that I actually, with the elementary calculus people, I call it the Black Knight theorem. And yeah. I'm actually thinking about John Cleese and Graham Chapman. Do I have the names right? And if you have a copy of VCT, you can go to the chapter 9 and click on this item there. And it's all the imagery of King Arthur going with a coconut and reaching the bridge. And there is John Cleese standing there, and he won't move aside, and he says, "I stand aside for no man." Definitely worth looking at this. And in the Monty Python version, Arthur cuts off the Black Knight's arms and legs, and he's still calling, "Come back and fight, you coward," right? Anyway, the Black Knight is really what you might call an upper bound. It fails to be an upper bound if you can cut off its arms and legs, and he yells after you, come back, you coward." It's too late, you're gone, you see? Right. So let me tell you something here. Part 1. An increasing sequence that is unbounded above. Okay? You should be feeling comfortable. Yes? I hope. All right. So, an increasing sequence that is unbounded above. Before I say anything, what does your intuition tell you? An increasing sequence that is unbounded above. This is where Arthur beats the Black Knight. What is it? What happens to an increasing sequence that is unbounded above? Right? Tends to infinity, right? Okay. Right, here we're going to go. We assume that sequence xn is an increasing sequence. You know what increasing means? x1 is less than or equal to x2, less than or equal to x3, less than or equal to x4, and so on. And for every n, x sub n is not smaller than, not bigger, than x sub n plus 1. That as you go from x sub n to x sub n plus 1, you go up, or at worst, you remain the same. See? Increasing. Doesn't have to be strictly increasing. It might be, but doesn't have to be. See? Increasing sequence. And that sequence xn is unbounded above. I'm changing color. If I can get it to come. There we go. We actually mean that the set, this, is called the range. The range of the sequence is unbounded above. That's really what I mean. But we will just say the sequence is unbounded above. What does that actually mean, the sequence is unbounded above? It means every number must fail to be an upper bound. No matter what number you take, its arms and legs will get cut off. You see? The number will fail to be an upper bound. We are going to prove that x sub n must tend to infinity as n tends to infinity. Okay? I'm changing color again. This is not part of the proof, I'm just talking to myself. We need to prove that. Okay, what are the ways of expressing the condition that a sequence tends to infinity? What does it say? For every neighborhood u of infinity, the sequence is eventually in u. More useful is to work with inequalities. Haven't I been saying this to you? For every real number w, the sequence is eventually in the stick, w comma infinity. Do you understand? We want to prove that for every number w, the sequence xn must be eventually in here. Okay? I'm just saying that to tell myself what I need to do here. If I don't know what my task is, I don't know what to do. So often, students write stuff for me, and they write all kinds of statements. And I say, but you're not telling me what your objective is. That's why you lost. See, I'm asking myself, what am I trying to prove? I think about what the definition says. We need to prove that for every number. Okay, how do you prove for every? Suppose that w is a number. See? Okay. Now I'm going to tell you something. Using the fact that w fails to be an upper bound of sequence xn, how do you know w must fail to be an upper bound of sequence xn? Because there are none. There are no birds to fly. No birds were flying overhead. There were no birds to fly. Okay? From the walrus and the carpenter. Who knew that? Need to read The Walrus and the Carpenter. Anyway, it's not as important as Humpty Dumpty and the Mad Tea Party. Anyway, using the fact that W fails to be, well, what can you do with the information that a number fails to be an upper bound? You can choose a member that's bigger, right? Let me talk to you. How would you use the information that some number was less than the least upper bound of a set? What do you know about a number that is less than the least upper bound of a set? What do you know? Less than the least upper bound can't be an upper bound of the set. Many people going wrong. Less than the least, it's not one of them, right? Okay. Using the fact that W fails to be an upper bound of sequence Xn, choose an integer, a big N. It will be automatically positive, by the way, because I'm about to refer to X sub big N, right? This is before you can jump on me, okay? But you're right. Choose an integer big N such that X sub that big N is bigger than W. Now, remember that sequence is increasing. For every integer n greater than or equal to big N, let me tell you what we know. We know that X sub n must be at least as much as X sub big N because the sequence is increasing. And X sub big N is bigger than W, so therefore the sequence has entered the interval W comma infinity, never to escape. You see? And that's the end of the proof. You see? I've just said, suppose that W is a number, and I've just proved that the sequence is eventually in the interval W comma infinity. Right. Now let's talk about an increasing sequence that is bounded above. Huh? Okay. So what do you think happens to an increasing sequence that is bounded above? We assume that sequence Xn is an increasing sequence, and that sequence Xn is bounded above. Okay? So it's bounded above. It's not going to go to infinity, but it will have a limit. What limit? It's going up, up, up. Where's it going to go? Where's it going to go? To its supremum. See? So I will tell you something. We are going to prove that Xn tends to, well, I think that I will say that the sequence Xn converges. I just prefer to write it like this: converges to its supremum. It slightly decreases the amount of notation on the screen. Okay. Okay. I'm going to give a name to the supremum. We write. What does write mean? We write as a definition. See, we write W equals the supremum of the sequence. Strictly speaking, the supremum of the sequence is the supremum of that set. You sometimes call this the supremum of the sequence Xn, but I decided just to be extra careful with you and say that means the supremum of the range of the sequence. Okay? And we want to prove that that X sub n tends to W as n tends to infinity. Are you all with me? This is the job. Okay, we are going to prove, I'm changing color to this color, and I'm going to say we want to prove that for every positive number, called whatever you want to, please get these letters correct. That is epsilon. The easiest way to type with Scientific Notebook is to get into the Greek keyboard either this way, okay, like this, you watching? Or Control G, the next one character you type is Greek. And you can get the epsilon by typing E then, see? Learn how to type epsilon and delta, for heaven's sake. I get some very strange symbols from some of you. Okay, we want to prove that for every epsilon greater than 0, the sequence xn will be eventually in the interval center x radius epsilon. You understand? I'm going back to the yellow. Oh, it's called W. Sorry. It's called W. Thank you. All right. So how do you prove that something happens for every positive number epsilon? Suppose that epsilon is greater than 0. That's how you prove it. Okay? Now I'm going to draw you a bit of number line. I'm going to show you W minus epsilon and a bit of number line, and then I'll show you W and a bit of number line, and I'll show you W plus epsilon. See? And I want to tell you something. This region up here is an absolute wilderness. There's nothing of any interest up there, because W is an upper bound of the sequence. Are you listening to me? The sequence never goes up here. The business part of this red interval is down there, you understand? And I'm going to tell you something. Since W minus epsilon, since W minus epsilon is less than W, what can you say about a number that is less than the supremum of a set? A number that's less than the supremum of a set, we've had so many proofs like this, is not an upper bound of the set. Don't tell me anything else. Don't tell me you think it belongs to the set. Not an upper bound. That's what we know. Since W minus epsilon is less than W, we know that W minus epsilon fails. I'm writing much more here than we would write for the proof. I hope you understand that I am not producing for you in this room a gold standard proof, the proof that you would write. The proof that you would write for this is not what I'm writing for you here. I'm trying to put something in your heart. And if you ever find that you're writing a proof by trying to reproduce my steps, you are going wrong. That's a first sign of somebody who's struggling, you understand, and probably making a mess. Don't do that. You must know why you're saying what you're saying. Since W minus epsilon is less than W, we know that W minus epsilon, what's the F? Fails to be an upper bound of the sequence, right? Right? Well, what can you do with the information that a number is not an upper bound? You can choose, right, a member of the set that is bigger, right? Choose an integer, a big N, such that W minus epsilon is less than X sub big N, right? Now let me tell you what happens. Whenever N is greater than or equal to big N, let me tell you what I know. W minus epsilon is less than the number X big N. Fair enough? The sequence is increasing. If n is greater than or equal to big N, x sub big N is not more than x sub n, right? That can't be more than that can't be more than W, because W is a known what? Upper bound of the sequence, and that in turn is less than W plus epsilon, you see? So this is what you call gotcha, you see? The xn is checked into that interval, never to check out. The interval has become what I like to call a roach motel, but I don't know if they still have that ad on TV. They used to advertise this thing called a roach motel. They said the roaches check in, but they don't check out. I don't know if you saw this. Anyway, so this shows that sequence xn is eventually in this stick, which is what we had to prove. Now let me tell you something. The entire latter segment, approximately 60% of Calculus 2, does nothing but talk about this pair of statements. Calculus 2. What is Calculus 2 doing? It's talking about these two statements. Not Calc 1, not Calc 3, Calc 2. The heartland of all that stuff about infinite series with comparisons, integral comparison, and the ratio comparison, and the comparison between two series. The whole idea is when you have series whose terms are non-negative, the more you add, the more you get. The sum increases. And if it's increasing, it either tends to infinity or it tends to a finite limit. When it tends to a finite limit, your series is convergent. When it tends to infinity, the series is divergent. Depends whether the Black Knight or Arthur wins the battle, see? And the comparison idea is if your series is underneath one that is not going to infinity, then it can't go to infinity. But if it can't be underneath such a one that doesn't go to infinity, then it breaks through and it goes to infinity. Or if it's above one that's going to infinity, then it gets pushed to infinity. This is what Calc 2 is all about. There's nothing else in Calc 2. That's what Calc 2 is. It's this principle. And so the missing ingredient in Calc 2 is this understanding. Why don't we finish this in Calc 2? Because we have to talk about supremum. You see? That's the difference. The purpose of this course is to make the elementary calculus sequence make sense. And this is an item from Calc 2. So what about the items from Calc 1? They're too hard. They're more advanced than this item in Calc 2. Functions. Continuity, maxima and minima of functions, derivatives, mean value theorem, all that stuff, that's harder. Well, in the elementary calculus, what looks easier is what actually in more advanced mathematics is a little bit harder. So we have to reverse. Anyway, we have to get going. So this is the stuff about monotone sequences. Look carefully at my picture. Do you see this? Crossed out. I'll tell you why. These are put in to make the reviewers happy. This stuff involves the use of the computer algebra system in Scientific Notebook to go and play and get all kinds of cute stuff. And some people are very thrilled about this. It will waste our time. I never do that. Okay? So that's why it's out. I have to put certain things in, otherwise people won't use my book. Okay, doesn't mean I agree. So I put all sorts of junk. And so that's the Black Knight theorem. Now we are going to study the other item that we're studying today is called the Cantor intersection theorem. And I need to give you two very important examples to motivate something I want to tell you. So here is the first one. Is that how you spell first? Please look at the definition. E sub n equals the interval that runs from n to infinity. I left out the infinity, all right? For every positive integer n. Do you notice that every set E sub n is non-empty? Boy, is it ever non-empty. It's a long, long interval, is it not? And every set En is closed. Do you notice this? Well, the complement of this interval is the set of real numbers that are less than n. That's a well-known open set, you see. So En is closed because its complement is open. And notice, please, that if you take the intersection n equals 1 to infinity of En, which I could write like this, just write in the value of En. I'm just trying to get this thing to come and copy here. It's empty. I'll tell you why. Because you give me any real number, what does the intersection mean? Who gets to belong to the intersection of a bunch of sets? What does it take for a number or any object, a chicken or whatever it is, to belong to the intersection of a bunch of sets? It's got to belong to every one of them, isn't that right? Well, if you take a real number x, aren't there integers n that are bigger than x? And as soon as you look at an integer n above x, then x will not belong to that interval. Do you understand? No real number can belong to every one of those intervals, because whatever number you take, you can always take an integer n that's higher, and the interval from n to infinity doesn't have your number in it. You see? The intersection of these sets is empty. I wonder if you mind closing the door for me. Push the handle hard up so we don't lock anybody out. As you've heard me say before, I like to lock you in but not lock you out. Okay? I'm a kidnapper at heart. All right. So the fact is that I've given you a sequence of sets that are all non-empty, all closed, intersections empty. Finally, please note, see how polite I am. Please note that the inequality E sub n, E sub n plus 1 included in E sub n, that inequality holds for every n. That, I mean, what is E1? E1 is the set of real numbers that are greater than or equal to 1. What is E sub 2? It's the set of real numbers that are greater than or equal to 2. Isn't that a subset of E sub 1? What's E sub 45? It's the set of real numbers that are greater than or equal to 45. And E sub 46 is the set of real numbers that are greater than or equal to 46. That's a subset. You understand? And this says that the sequence of these sets, this is not a sequence of numbers, it's a sequence of sets. See? That sequence is what we call contracting. A sequence is contracting when the second one is a subset of the first one, and the third one is a subset of the second one, and the 99th one is a subset of the 98th one, and the n plus 1th one is a subset of the nth one for every n. You see? This is an example of a contracting sequence of sets. Contracting. Each one is a subset of all those that came before. You understand? E sub 55 is a subset of all the ones that came before. E1, E2, E3, E4 up to, right? Contracting sequence of non-empty sets, non-empty, right? And they're all closed, and the intersection is empty. Do you notice? Right. Here's the second example. Second example, I think that might look a bit nicer too. Okay? Right. Here's my example. In this example, question?
About the first one. So does that mean that each sequence has
There's only one sequence. I've got a single sequence, E1, E2, E3, etc.
Right.
Each set, do you mean?
Yeah, like each set of those sequences.
No, each, for every n, the set En.
Okay.
I've got to stop here. I'm sorry if I'm giving you a hard time,
But
right?
En has elements, right?
Oh, absolutely.
So does those elements have a lower bound?
Well, actually, you don't want to say that. You want to say, does the set En have a lower bound? The answer is yes, because for every n is the least member of En. So, in fact, En is bounded below, and the greatest lower bound, actually the least member of En, is n. But if you ask me, does the set En have any upper bounds, I will answer no. Every one of these sets is unbounded above, but is bounded below, okay? Don't ask me if the elements have lower bounds. It's the set En that has a lower bound for each n. See? Let's get the language right. You'll thank me if I'm hard on you now, okay? Because I know you can do that. Okay. So I hope you all listened to what Mace had to say. She asked whether for any given n, whether the set En is bounded below or whether the set is bounded above. That's more or less what I think you were asking. And my answer is, look, the set has a least member. Each set En has a least member. You have to know which n you're talking about, you see. For any given positive integer n that you happen to be considering, the set En will have a least member, mainly the integer n. But it's unbounded above. Okay? Now, in this example, we define E sub n to be equal to the interval. I'll take the interval running from 0. This doesn't look like 0. That's how we write 0. 0 to 1 over n. Let's see a few facts. Note that every set En here is non-empty. Yes? And bounded, because 0 is a lower bound and 3 is an upper bound. You want to do better? 1 will be an upper bound. Actually, you want to do better? For any given n, 1 over n is an upper bound. See? Okay. Non-empty and bounded, and that the sequence of these sets, the sequence big En, that sequence is contracting. I hope you understand that if you look, here is 0, and here's a bit of number line, And here's 1 over n. Oh, what have I done? Here's 1 over n. See? And here's a bit more number line. And here is, oops, 1 over n plus 1. Oh, I've got them in the wrong place, haven't I? You go here, you go here. You understand? Isn't it like this? The sequence is contracting. If you make n bigger, the interval from 0 to 1 over n gets smaller. Do you understand? And again, we have, let's have a look at the intersection. Of course, this is the formula for the En here, right? Why is this intersection empty? Well, if you take any real number, if that number is less than or equal to 0, it doesn't even try to get in, right? But if you take a positive number, for large enough n, won't 1 over n be less than your number? And your number is not in this interval. Do you understand? You take any number x that is positive, for large enough n, isn't 1 over n smaller than x? I'll tell you something. All you have to do is make n greater than 1 over x. Haven't we done this a zillion times in the course? So no matter what number you look at, you can be sure that that number will fail to belong to the intersection. It can't possibly belong to every one of those sets. Fair enough? And in this case, I'm showing you a contracting sequence of non-empty bounded sets, and the intersection is empty. Here in the first example, we had a contracting sequence of non-empty closed sets, and the intersection was non-empty. Excuse me, what do you call this? Empty. See? In the second example, we had a contracting sequence of non-empty sets that were bounded. In the first example, we had a contracting sequence of sets that were non-empty and closed. And in both cases, the intersection is empty. I'm now ready to state the main theorem. Maybe you can guess what it is. You're going to suggest the theorem to me?
No, I was going to ask you another question about it. Like, excuse me, in the first example, whenever you have that the sequence En is contracting, excuse me.
No, we're looking at one particular sequence, and I'm saying that sequence is contracting.
Right,
not whenever a sequence is contracting. We're not saying every contracting sequence does something. This is an example of a particular sequence that happens to be subtracting.
Like, could you also say that for every number that is less than 0 all the way to n, would that sequence also contract as well?
There's only one sequence here. I've got one particular sequence, and this sequence is a contracting sequence. I've got a definition. E sub n is the interval running in infinity for every positive integer n, and I'm saying this sequence is contracting, and I'm saying that every one of these sets En is closed, and they're not bounded though. Okay? That's all that's important. Okay? So I want you to focus on exactly what we have. What should the theorem say? This is the big question. Statements of the Cantor intersection theorem. I've set you up to want to state it. What should it say? I've said if you take a contracting sequence of non-empty closed sets, the intersection is in danger of being empty. If you take a contracting sequence of non-empty bounded sets, the intersection is in danger of being empty. What do I hear? Somebody, talk to me. You want to talk to me? What?
Sequence that is both closed.
A sequence, not the sequence is closed, the sequence of sets, a contracting sequence of sets that are non-empty and both what? Closed and bounded, right? You know, because I dangled it before you. In the one case they were closed, in the other case they were bounded. But the closed ones weren't bounded and the bounded ones weren't closed, you see. So I've kind of set you up to expect, right? Well, is that the theorem, or do we need some extra sneaky addition to make it work? Well, I'll put you out of your misery. That's the theorem. We assume that sequence En is a contracting. What does contracting mean? That every one of these sets is included in all the earlier ones. You understand? Contracting sequence of what? Non-empty, closed, bounded sets. We are going to show that the intersection of all of these sets must be non-empty. You understand? You understand the statement? I haven't done it yet. I'm changing color before I write the proof. I'll tell you what. I'll make this part white and this part yellow. There. Oh, wow. There. Okay. How does one prove that a set is non-empty? What is the strategy for proving that a set is non-empty? Give an example of a member. That's the only method Jonathan Lewin knows. You want to prove that something exists? Give an example. Bring one in through the door on a string. You can show me that a unicorn exists. I wrote non-empty. That's an unequals. Not the empty set. There, in the other cases and examples, we got the empty set. I'm now going to claim unequal to the empty set. Okay? That's an unequal sign, most definitely. That if you have a contracting sequence of non-empty, closed, bounded sets, you've got both closed and bounded, everything's good. The intersection must be non-empty. So I'm going to announce we need to give an example of a number that belongs to every one of the sets E sub n. It belongs to En for every positive integer n. You understand? That's my, that is what I need to do. I'll tell you what, I'll write that in green and then we'll begin the proof. We need to, and the color is as much part of your notes today as anything else. You know what I'm writing, the actual words are 10% of what I'm writing. The color is the other 90%. Okay. So here we go. We need to give an example. And this is how we do it. We're going to do it today. In a former life, we proved that whenever a set is closed and non-empty and bounded below, aren't these sets bounded below? Because they are bounded. Bounded means bounded both below and above. I need that, you see. When a set is non-empty, closed and bounded below, the set has a least member. I want to remind you, one of the things that I taught you, we did in great detail in this class, and I stuck it in your preview. I said, if you have a set, you'll find it in the lecture notes. If you ever have a set that is non-empty and bounded, the supremum must be close to the set, and the infimum must be close to the set. Isn't this what we made big stuff about this here, haven't we? So what do you know if the set's closed? Numbers that are closed have to be long, right? So I want to tell you that for every n, we know that the set E sub n must have a least member. Now listen to me. That's what I've written for you here. It doesn't mean that when you're writing the proof that you write these words. If you write to me, for every n, we know that E sub n has a least member, I will say, excuse me, how do we know? I'll be suspicious of you. Or maybe in an exam, maybe there'd be an A part and a B part, and in the A part I would ask you to explain to me why the infimum of a non-empty bounded set must be close to the set, and in the B part I'll say, what happens if the set is non-empty and bounded and closed? And you say, well, now the infimum has to belong, you see? Therefore there's a least member. Then we come to this. Maybe I'll break it down for you. Here, I'm not reinventing that wheel, because we'll sit here till midnight. Well, I will, and then you'll walk out on me. So okay. So we need to know that the set, we know that the set En has a least member. Right, well, I'm going to give a name to the least member. For every positive integer n, if I'm giving a name to the least member, what word is it? Is it define or choose? Who says define? Who says choose? It's defined, because the least member, the minute you see the definite article, you know it's a definition. You know, if you were to say for every n, choose a lower bound, then, well, yes, I don't want a lower bound, some arbitrary lower bound. I want the least member. For each positive integer n, we define x sub n to be the least member of the set E sub n. You all with me? Now I want to tell you something here. Given any positive integer n, we know that the number x sub n plus 1, what is going on here? Is that any better? The number x sub n plus 1 is a member of E sub n. How do you know? X sub n plus 1 belongs to E sub n plus 1, anything that belongs to one of these E's belongs to all the earlier ones. Isn't that right? If you belong to E sub 19, then you belong to E sub 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. You see? For every n, x sub n plus 1 is a member of E sub n, and x sub n is the least member of E sub n. Isn't that right? And so, let me tell you something. this guy is the least member of E sub n. And this one is some unknown member of E sub n. Well, the least one can't be any more than some other member. You understand? The youngest person in this room, that's me, can't be any older than somebody else in the room. Okay? So I won't quote Groucho Marx this time. Not going there. All right. So for every n, x sub n is the smallest member of En, and x sub n plus 1 is some other member of En. So therefore, x sub n must be less or equal to this. And you know what? Therefore, sequence xn is increasing. Isn't it? It's an increasing sequence, right? I also want to tell you that we also know that x sub n belongs to the bounded set E1 for every n. And we know a jolly lot more than that. I mean, x sub 2 belongs to E2, which is a subset of E1. And x sub 3 belongs to E sub 3, which is a subset of E2 in E1, you see? And x sub 99 belongs to E sub 99, which, take a deep breath, belongs to E1, E2, E3, E4, E5, E6, E7, all the way up to E98, right? Every one of these xn's belongs to E1, right? Therefore, the sequence xn is bounded. It's a sequence in the bounded set E1. You understand? So it's bounded. Aha. Therefore, how do you spell therefore? Therefore, sequence xn is convergent. An increasing sequence tends to infinity if it's unbounded above, and tends to a finite limit, mainly its supremum, if it is bounded above. This sequence is convergent to its supremum, actually. We call its limit x. Okay? I'm going to just switch to a bit of green. I am going to explain why this number x must belong to E sub n for every n. That's what I'm going to explain. If I do that, then haven't I fulfilled my promise, which was to give an example of a number that belongs to En for every n. This is it. This is the number. If I succeed in doing this, then you can go home, actually. Right? Let's see. I need to explain. Now, let me stay in the green for just a little bit more. I need to explain why for every, and I don't want to use the letter n. Too many n's already. I could use a j. Let's use a big N. For every positive integer, I was going to use a k. Oh well, let's use big N. I need to explain why for every positive integer, big N, we must have, what the hell happened here? We must have this particular number x belongs to E big N. Isn't this my job in order to prove that x belongs to every one of those E's? Got to prove that for every positive integer, whatever you happen to call it, Charlie, X will belong to E sub Charlie. I used a big N, okay? I nearly used a K. All right, I'm stuck with big N. Now I'm going to the yellow. How do you prove that something happens for every positive integer big N? Suppose, how do you prove for every? Say, suppose that big N is a positive integer. Okay, folks? Now I want to tell you something. Whenever n is greater than or equal to big N, we know that x sub n must belong to E sub n, which is a subset of E sub big N. Isn't that? What the hell did I do? Don't we know that? For every n greater than or equal to this particular integer big N, x sub n, which belongs to its own En, which is a subset of E big N, x sub n must belong here, right? And so we know that sequence xn is eventually in E sub big N. Isn't that right? And therefore, the limit x of the sequence, of this sequence, must be close, right? Must be, I'm going to do better. This is be close to E sub big N. That's what I've written. I'm going to erase this. E sub big N is closed. So when can't we do better? Must belong to that. Yes? Isn't that what I told you? If you have a sequence, even frequently would have been good enough. If you have a sequence frequently in a closed set and the sequence happens to have a limit, then the limit has got to belong to that set. The limit's got to be close to the set, but the set is closed. This is where I'm using the fact, this is the only time I'm using the fact that the set is closed. Therefore, okay? And that's the end of the proof. What did I say in the green is my job? To prove that for every positive integer big N, x must belong to big N. Now what have I got? I said suppose that big N is a positive integer. Now, whenever n is greater than or equal to big N, xn belongs here. Well, the sequence xn is eventually in that set. Therefore, since the sequence has a limit, I can tell you that the limit is close to that set. But I can do better than that, because the set is closed. So therefore, close to the set means in. When you're close to the set and the set is known to be closed, you've actually got to be an honest-to-goodness member of the set. You see? So I've said, suppose that n is a positive integer. I've just proved to you that this number x has to belong, the limit has to belong to En. That is right. Now we have to go back through this proof. Listen very carefully to me. We are starting with a sequence of sets. And what do we assume? We are looking at a sequence of non-empty, closed, bounded sets. And the sequence has to be contracting. We've got a contracting sequence of non-empty, closed, bounded sets. And what's our job? Our job is to prove that there exists a number that has to belong to every one of these sets. A number, we're looking for a number called Charlie, such that Charlie belongs to En for every positive integer n. So how do you prove that something exists? You pull one out of your pocket. And the pulling out of the pocket required a few big guns. This is what we did. We started by saying, if you look at any integer, positive integer n, I know that the set En is a non-empty, did it say non-empty? Bounded closed set, it's bounded below, and therefore it's got a least member. A non-empty set that is closed and bounded below has a least member because of the old principle that you and I have done over and over and over again in this room, that when you take a set that is bounded and non-empty, the inf of the set must be close to the set, and so for that matter is the soup close to the set. But if the set is closed, then when you say close to the set, that really means belongs to the set, and therefore what? Therefore, every closed set, non-empty closed set, bounded below, has to have a least member. I am making a definition. Define x sub n to be the least member of En. You can't do this until you are absolutely solid in your own mind that you understand why the set En has a least member. So this sits on the shoulders of all the previous lectures, you see. No proof sits on its own. Sometimes people ask me to read a particular proof and they say this is okay, and then I start asking, well, you've just used a certain piece of information from earlier work. Are you just quoting that, or are you just saying it to find out if you can get it by me, or can you get it by you? That's the question. Not can you get it by me, but can you get it by you? Do you know why what you're claiming is valid? And different people can say the same thing, and from one person, because of other things the person has said, I would say, yeah, that's fine, that's obvious. Somebody else can say it, and I'll say, well, but you haven't said enough to me. I don't know that you see this. To take an extreme case, I took a course called 742, which was the second algebra course in graduate school, from the same professor, Charles Holland, from whom I'd taken the first course. And I needed to make use of a certain facts that happened to be a question in his final from the first course. And I was in the final of the second course. I needed to make use of the fact. I said, Professor Holland, you are perfectly aware that I don't know how to write this proof, because as it happened, it was a question in your final from the first course, and I chose that question and did it. And I don't think you want to see this again. And when I got this back, he said, you are quite right. I don't want to see this again from you. You see? I quoted my own proof from an earlier place. Otherwise, I'd have had to write it. You see? Okay, that's the rule in mathematics. Something is, let me tell you when something is obvious. A statement, if two people called A and B are talking to one another, A is talking to B and says, the statement is obvious. What does that mean? Firstly, there's three requirements. Three. A must know how to prove it. Second requirement. A must have confidence that B knows how to prove it. Third requirement. A must have confidence that B trusts A enough that when A says, I know how to prove it, that B says, yes, I trust you. If you tell me you know how to prove it, I know you can prove it. If any of those three conditions is not there, the thing is not obvious. It has to be written out. That's what obvious means. Some people think obvious, the professor doesn't know how to do it. In some courses, that may have some truth. Okay. There's a famous story about G.H. Hardy, great English mathematician, that he was talking to students in some kind of advanced course, and he said, it is obvious that such and such. And according to the story, who knows this? Hardy said, a student said, Professor Hardy, is that statement obvious? And Hardy said, I have to think about this. And he left the room and sat for 10 minutes in his office. came back and said, yes, ladies and gentlemen, it is obvious, and continued his lecture. So anyway, the first thing we did was we defined x sub n to be the least member of En for every n. Then we made the observation that this sequence we have just constructed is an increasing sequence. Then we pointed out that this sequence is a sequence in the set E1, and E1 is bounded. So therefore this is an increasing bounded sequence. By the Black-Knight theorem, the sequence has to converge, right? We then gave a name to the limit of the sequence. There are all sorts of steps here. You must make sure that you don't just recite these things and say, this is the proof, this is what Lewin said, therefore it's okay. It's okay if you can see that it's okay. We gave a name to the limit of that sequence. Then we say, okay, I'm now going to prove that this number x will belong to every one of the sets En. Suppose that big N is a positive integer. It is my job to prove that x, this limit x of the sequence, belongs to En. Well, let me tell you something. I know that whenever n is greater than or equal to big N, I know that x sub n, which belongs to its own En, certainly belongs to the earlier E big N, you see? Therefore, I know that the sequence xn, is eventually in E big N. I don't even need that much. Frequently would have been good enough, you understand? I have a luxury eventually. A sequence with a limit that is frequently in a given set, if the set is known to be closed, the limit of the sequence must belong to that set, because the limit has to be close to the set, but I said the set is closed. Therefore, this number x must belong to E sub big N, and I started with suppose, so I've just proved for every positive integer big N, x belongs to E big N. Therefore, this intersection is non-empty because I am in possession of an example of a number that belongs. This Cantor intersection theorem is probably the key reason why we have been studying sequences throughout the last few weeks. We have only one more thing to do with this course. To make use of the Cantor intersection theorem to show you, to answer some questions that I've dangled before you already. When I asked you, let me remind you, I said if you take a bounded sequence, do you think that a bounded sequence has to have a partial limit somewhere, or do you think it can be so wild that it just manages not to have a partial limit? And the answer is it's got to have one, and we'll be looking at the existence of partial limits, which will be our last topic. See? So you've got a bit of time to study this stuff, because I'm sorry to say that you're not going to see me for new material until a week from Monday. Because Monday I'm not teaching, remember? And Wednesday, unfortunately, I wish we didn't have to have a midterm. You know the funny thing that I did a 4382 once, and 12 people came into the course. It was a bumper year. And I walked into the 4382, and I looked around the room, and I saw who was there. And they were survivors of 4381, strong enough to dare to add 4382 to their degree. You understand, I'm in business in 4382. I'm not Mr. Nice Guy like here in 4381, you see? Then we move and we do stuff, you see? So I looked around and they all choosing to make their degrees harder. Now look at approximately 12 people. And I knew all these people are going to be fine. And I had this course outline, printed actually in those days before I knew how to make websites. And I walked ceremoniously up to the recycle bin and dumped all my papers in the recycle bin. And I said, here is my course outline. There will be no midterms. There will be no final. You all know that you have grades of A. Let's do math. And their mouths dropped open in horror, because now it became a matter of honor. And I had 12 people working very hard. That's the way I like to do. That's the way I like to work with people. I like to have people really, really putting their all into it, not because they have to, but because they're to put in the words of Thomas Gray from the Elegy in a Country Churchyard, hearts pregnant with celestial fire. Not a bad poem to read, by the way. That's all I have to say today.